Okay, so in previous lecture, we have talked about the theorem which says that, which gives the classification of subgroups of cyclic group. And the theorem said, fundamental theorem of fundamental theorem of cyclic groups said every subgroup of a cyclic group is cyclic. And if you know the order of if you know the generator of any cyclic group and the order of the group, then you just need to find the divisors of the order of the group, and then every divisor of the order of the group will give you a subgroup for that particular group. That's the theorem. Corollary actually said that for each positive integer, positive divisor k of n, the set nk, n quotient k is the unique subgroup of Zn, okay, of order k. And that we have did here. And then if you want to find the generators of the subgroups of order n inside Zn, what you need is to find that what is the quotient n over d, and then you need to do something like that. Okay, then we define the Euler phi function. Euler phi function counts the number of elements, number of positive integers less than n and relatively prime to n, and it gives you the order of the group u of n. Okay, now we will give you the theorem which says, and this theorem is about number of elements of each order in a cyclic group. So first you found out the orders of the subgroups, and then subgroups. Now you will find out what are the orders of elements inside the cyclic group. That's very good to know. And that you can get by a statement says, if D is a positive divisor of n, the number of elements of order D in a cyclic group of order n is nothing but phi of D. So this gives you how many numbers, what is the number of elements of order, of certain order in a group, of a certain order in a group, okay? So the number of elements of order D in a cyclic group of order n is nothing but phi of D. Interesting. And you can say, and this can work for a lot of them. So let's take a big group and then try to find out how many numbers of certain order are there in a group. So proof is related on other proofs. So I'm going to skip that and I'm going to focus on the learning and understanding. So notice that for a finite cyclic group of order n, the number of elements of order d for any divisor d of n depends only on d. So example, so thus, so if you take Let's say we want to find number of elements of order 8 in what? In Z8, Z640, Z4, actually 80,000, are nothing but pi of 8, which are 4. So there are 4 elements of order 8. That's crazy. If you know in a Z 80,000, how many elements are there of order 4, order 8, and you just know the answer that there are only 4. It's just crazy result. Amazing result. Okay. The corollary is, although there is no formula for the number of elements of each order for an arbitrary finite group, we still can say something important in this regard. And that we can say in this corollary. Corollary gives you number of elements of order B in a finite group. Okay. So in a finite group, the number of elements of order B is not is a multiple of phi of t. That's also something which we should think of. And I would like to prove this thing. So the proof is a number theoretic proof and a group theoretic proof. So bear with me. In a finite group, so if a finite group has no elements of order B, the statement is true. Since phi of d divides 0. Perfect. Now suppose that now suppose that there is an element from the group and its order is B. Then by theorem, 4.4, we know that the set generated by A has phi of the elements of order D, or if all the elements of order D in G are in the set generated by A, we are done. So suppose that there is an element B in G of order D that is not in the set generated by A, then the set generated by B also has phi of D elements of order D. This means that we have found we have found 2 into phi of D elements of order D in G, provided that the set generated by A and the set generated by B have no elements of order D in common, right? Now, if there is an element, if there is an element of order D that belongs to both the set A and the set generated by B, then we have the set generated by A is equal to the set generated by C, which is equal to the set generated by B. So that B needs to be inside the set generated by A, but which is a contradiction. Now, it is a contradiction. Now, continuing in this fashion, we see that the number of elements of or B in a finite group is a multiple of phi of t, and that is the proof. Now, it is very important and useful result and good to know result that if you don't even know what how many numbers are there of order something in a general finite group, but you can know that it should be multiple of something. Perfect. So on its face, the value of the theorem 4.4 and its corollary seems limited for the large value of n, because it is tedious to determine the number of positive integers less than or equal to n and relatively prime to n by examining them one by one. However, the following properties of the phi function make computing phi of n simple. So that is, so you can say for any prime p, phi of p power n is equal to p power n minus p power n minus 1, and for relatively prime m and n, phi of mn is equal to phi of m and phi of n. Thus, in example way, phi of 40 is actually equal to phi of 8 into phi of 5, and which is nothing but 4 into 4, which is nothing but 16. Means phi of 40 is 16. Very good. Similarly, phi of 75 is actually equals to phi of 5 square into phi of p. That is nothing but 25 minus 5 into 2, which is equals to 40, because 5 is a prime, and you can compute that phi of 5 square is with the formula phi of p of n, p power n, and then you can do. Now, the relationships among the various subgroups of a group can be illustrated with a subgroup lattice of a group. This is a diagram that includes all the subgroups of the group and connects a subgroup H at one level to a subgroup K at higher level with a sequence of line segments if and only if H is a proper subgroup of K. Okay. Although there are many ways to draw such a diagram, the connection between the subgroups must be the same. Typically, one attempts to present a diagram in an eye-pleasing fashion, and the latest diagram of Z30 is shown below. So let's try to draw the latest diagram of Z30. I'm going to keep these empty at this time. Then you can also write something and give a bracket, a line to this, and then you can say something here and also here, and two more which are going to be okay. Now let me adjust them. These two are fine. Okay, I should pick this and put it here, and then pick this, put it here. Okay, right. Now this is one here, this is two here, this is three here, not three, but five. This is three here, this is 10 here, and 6 here, 15 here, and 0 here. Now, there's a reason to place them like this, and the reason is that you can say these two are subgroups of each other, these two are not each other. One is a subgroup of 2, is here, and then you can say here, here, 3 is not in 10, and then we have here, we have here, and we are from here to here. So 1 contains 2, 5, 3, but it also contains all of other. So 2 contains the subgroup 10, which is generated by the element 10, and 5 also contains that. 3 contains subgroup generated by 15 and 6. 15 and 6 contains the subgroup generated by 0. And 1 contains everything. So this is a subgroup lattice. This is a subgroup lattice of Z30. Okay. Now, the precision of the theorem 4.3 can be appreciated by comparing the ease with which we are able to identify the subgroups of Z30 with that of doing the same for, say, U of 30 or D30. And these groups have relatively simple structure among non-cyclic groups. And that we will discuss in later chapters. Thank you so much for listening. Hope you have a nice time learning group theory.